ether, a 6-membered ring that's a cyclic ether, is a pyran. Just like a 5-membered ring is a furan, like the tetrahydrofuran knows a little bit. And so you can protect an alcohol, as is shown here. Let's say you, for some reason you want to protect this alcohol. You can use this dihydropyran, or DHP for short, to protect it. And it will form a species like this, and then take this group off in the presence of acid as well. I actually bring this one up because I think it highlights kind of a nice feature or review, is that thinking about what is the mechanism of this. And so now notice we don't have any carbonyl groups here, so that's a little bit different. But how might this work? So let's take this species here in the presence of acid. And this is known as a vinyl ether, meaning that the vinyl means it's next to the alkene. So you have an alkene and you have the ether here, so it's a vinyl ether. And this brings back a nice concept from Organic 1, I think. And that in the presence of acid now, rather than protonating the carbonyl group, we've seen that you can add water, HBr, lots of things across double bonds. Let's protonate this species with the double bond. And a good question now is, where's the proton going to go? One side of what was the alkene is going to get the proton. The other side is going to be left electron deficient, or a carbocation. So we could put a carbocation here, that would be secondary. We could put a carbocation here, that would also be secondary. But that's actually where the carbocation goes predominantly. So that there's the proton, there's the carbocation. And it goes back to, as I mentioned, okay, one material, when in doubt, think about resonance, because this is actually a resonance stabilized carbocation. So that's energetically more favorable to form. Just put the hydrogen so it shows everything. So it looks like this. And this looks kind of like our carbonyl type group that we have. So now we can have our alcohol attack. Could attack either, of course, resonance structures are just totally made up. They're all happening at the same time. So let's have it attack on this side that we've drawn. So now we form a new bond here. This stuff is all the same. Positive formal charge on the oxygen. You can put the hydrogen in there to show. And then now all we have to do is deprotonate. And I'll be lazy, and it's going to give you this product. So this is one of those cases now where if you were to see this, and I actually had a problem like this on I think it was a homework set last semester with a different group. I remember it caused some grumbling. So I thought it was a good thing to see, because we actually didn't talk about it in class, and so it just kind of came out of nowhere. But if you were to see this product here, and this alkene, this is this vinyl ether in the presence of acid, the question might be, well, where do we start with anything like this? We've never seen anything like this before. But that goes back to thinking about some of these common trends. In this case, we don't have a carbonyl group to start with, but we have an alkene, it's vinyl ether, which we'll see again and again, and we could protonate it. That's what we see in the presence of acid. We need to think about which side of that alkene, what was the alkene, is going to get the carbocation. And it goes all the way back to thinking about resonance stabilization. Secondary here, secondary but able to be stabilized by resonance. And this is actually the major contributor, because everything has a full octet, so that goes back to that idea of resonance. And so now our nucleophile can attack, and then just end deprotonation that generate the final product. So you're right, Crystal. The carbocation will go on the most substituted alkene position. The carbon of the alkene that is the most substituted is the one that's better able to stabilize that partial positive charge. And then in this case, there's also resonance stabilization, because these two carbons here, without the oxygen, would be equivalent. So if we just had Yes, if we had a carbocation here, let's just put something over here to differentiate the two. So if we had this one. This would be a secondary carbocation. If we had a carbocation at this lower carbon, that would also be a secondary carbocation. So there would be no difference. Now, of course, it would be better to have the carbocation over here if you had a reaction that led to that product, because that's a tertiary one, more substituted, more stable, and we can go back to hyperconjugation as the physical basis for that. And now, in this particular case, we have this oxygen here. So this makes it a little bit more complicated, more exciting too, hopefully, in terms of thinking about resonance stabilization. Because now, if we have, let's just consider the other scenario. Let's put the hydrogen here and put the carbocation there. Now, that is a secondary carbocation, so that's better than primary. But in a way, that carbocation is just, it's stuck on that particular carbon. Now, instead, if we consider the top case, we have a carbocation in this carbon. It is also secondary, so that really doesn't distinguish between these two carbocations in terms of their relative stability. However, this carbocation is adjacent to this oxygen with these two lone pairs of electrons, which means that this positive charge does not reside solely on this carbon, but actually is resonance stabilized by drawing, and we can illustrate that by drawing a resonance structure where these lone pairs, this lone pair of electrons is used to form the resonance structure. Now, this is going off a little bit on something else. Remember that it seems unusual in a way that the most electronegative atom, oxygen in this case, compared to carbon, would be giving up its lone pair of electrons in this resonance structure to form this double bond. However, a driving force is that in this right resonance structure, every atom has a full octet of electrons. So I can draw in the other lone pair. Remember, things like oxygen and nitrogen, sulfur, those heteroatoms, they can have a full octet of electrons while still bearing a formal charge. And that's the driving force. Everything is happy, if you want to think of it that way, here having a full octet of electrons. Whereas this carbon it does not as well. So it's a bit of a tangent on carbocation stability, but it's a nice, I think, review of that concept. Okay. We'll go forward. So how about some other reactions? Abbas asks, should we draw the resonance structure in the exam? It's up to you if you want to draw the resonance structure or not in terms of the mechanism. You don't necessarily have to. I did this here for illustrative purposes and that, but if you don't, if you just had this alcohol attacking this species, that's certainly fine, right? Because these resonance structures, it's just something that we totally made up because we don't understand it. We can't explain things, and so then we just assume that these resonance structures. But remember, these are all happening at the same. It's not actually like flipping back and forth between the two. They're all present at the same time. That's just our tool to describe them.